So 3 professors are sitting in a bar. A physics professor, a math professor, and an engineering professor. And they're discussing how to calculate the volume of a little red ball. So the physics professor says, I'll calculate the volume, I'll submerge the ball in water and measure the displaced volume and calculate the volume of the red ball. Math professor says, well, I'll take the radius of the little red ball and use the
triple integral,
whatever, blah, 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 math equation for, as you can tell, I'm the engineer professor in this joke. Use the math equation to calculate the area of the volume of the little red ball. The engineer professor goes, well, I'll just look up the volume from the little red ball volume book. Engineers have a manual for everything. We don't actually calculate any numbers, we just look it up in our various books. Which takes us to the green book, the policy on the geometric design of streets and highways, where we're going to be looking up vertical curves. Yeah? All right. So, pop quiz. Horizontal curves go around, vertical curves go over or under. That's right. Okay? So, all this is. So, right, horizontal curve. Garbage. All right, here we go.
you got it. That was a vertical curve.
Yeah, it was parabolic.
You did a walk over.
Yeah, of course. The point was to throw it in there. It wasn't actually to get rid of it. Right? Horizontal curve, right? Looking at the road, you represent the car like that. All right? Vertical curve. I'll tend to draw them like this, and then I'll do vertical curve. Yeah? Up and over the hill. There's my grandfather's view. Okay?
So in this case, not up and over the hill.
Almost up and over the hill. It's American made. Come on.
That's true, that's true.
Okay, so that's what we're talking about today. All right? So, okay. So there are 2 types of vertical curves. All right? There's one where we go over, that would be a crest vertical curve, and there's one where we go under. Right? That would be a sag vertical curve. Right? Both have different sight distance requirements. But both are still designed for adequate sight distance. You must be able to bring your car to a stop on a vertical curve, sag or crest. Right? Sight distance can be maintained, speed must be reduced. This has an impact on the efficiency of the road. Vertical curves are parabolic, unlike horizontal curves. What does it mean when I say vertical curves are parabolic? Yes. Boop is right. Or boop. Boop. Okay, yeah. They have a square function in them, right? Whereas horizontal curves are just circles, right? Because sight distance requirements of crest curve and sag curves are different, they are designed differently, right? What are the sight distance problems of a crest curve?
You're sitting under you. You can see what's on the other side of the crest.
You can't see what's on the other side of the crest, right? You're coming up, even if it's a little one, there could be a car that's like right in between where you can't see it, or a ladder, or a pedestrian, or whatever. What are the sight distance problems of a sag curve?
There aren't.
But the
Well,
side-
yeah, there are. It's like the roof, maybe.
Or if you're like at the bottom and then
You
like
can't see the
you
taillights
can't see
on
what's
top?
above you.
Sight distance at night over and the presence of and obstruction.
It's literally on the board.
Awesome. Yes, you
She's killing it. Ryland's ready to go for this one. Ready. Thanks, Will. I'm very happy that this is being recorded for posterity. I'm going to be using this video 20 years from now. So when you're going downhill, you can see everything, yeah? Right, you have the advantage point of seeing everything. However, at night, you can't see everything. You can only see as far as your taillights, or as far as your headlights project in front of you. All right? Also, if you have like a bridge that you're going under or something, that's an obstruction to things on the other side as well. All right? So during the day, we actually have the curve that's in our way, and at night, we have to worry about headlights. Yeah. Now, you can say, well, why don't you just add lighting? Because lighting's expensive. You could, I mean, that's totally a reasonable thing to do. It's just very expensive, so you have to weigh that out. Okay. So, crest curves. All right, let's draw this out a little bit. Okay. So we have an initial road with an initial grade. We talk about grades? Represent grades as percents? Yes. Okay. We have an initial road with an initial grade. Yeah? We have to transition between grades. We have another part of the road that has a different grade. Right? So vertical curves are used to transition between grades, just like horizontal curves are used to transition between directions. Right? Horizontal transition between directions, vertical curves transition between grades. Solid exam question. Okay? So we have one grade here and one grade here. Right? This is the point of vertical curvature where we depart from the tangent to the curve. The point of vertical intersections where the two grades would intersect if they could, but they're not. And then the point of vertical tangent where we go back to the tangent side of the road. Yeah? Sound good? Okay. A crest curve has the PVI, the point of vertical intersection, above the ground. It's like in space somewhere, right? So you can see that here with a, here G1 is a positive value, here G2 is G2 is a negative value, right? It makes a clear crest curve, right? But you'd also have a crest curve where PVI is above the road with two positive grades, PVI is above the road with two negative grades. Yeah? Here's a sag curve with a negative grade to positive grade, right? We're going down and then we're going up, standard. But here's one with two positive grades because PVI is underneath the road. Right? The road's above here, PVI is under the road. Here, PVI is under the road. Here's two negative grades with PVI under the road. Yeah? So if I just gave you two grades, you could sketch those out and figure out whether it's a crest curve or a sag curve, yeah? Right? Power of deduction. Okay. There's like a mathematical way to do it, but just sketch it out. Okay. Here's kind of what the setup looks like. What's a datum?
A reference line.
Yeah, the data line.
Mechanical guys, nailed it. Yeah, just a reference point, sea level or zero or whatever, right? Oh, PVC, PVT, PVI, okay? Y PVC is the elevation of the point of vertical curvature. Right? Then we have a Y PVI, PVT. This little y is the difference. We don't really use it that much. All right. X. X is measured from PVC in the positive direction. It is the straight shot distance. L is the linear distance between PVC and PVT. Y is L, the linear distance between PVC and PVT for vertical curves. Yes?
Because it's used as station then?
Uses the stations, is pretty good. Remember, we station the road in plan view, top looking down, right? A horizontal curve in plan view looks like a curve. A vertical curve in plan view doesn't look like anything. It just looks like a straight segment of road, right? Because you can't see the elevations, right? That's how we're stationing this, so that's how L is. That's how L is defined. In a horizontal curve, plan view, we see the curve, we're stationing along that curve, right? We have to take into account that arc length. Here we do not take into account that arc length. It is the direct shot. Yeah? Good. Okay. So we have a G1, a G2, we have a back tangent and a forward tangent. All this fun stuff that we'll get to. Okay. All right, I already said all that. Okay. So, L is measured as a straight distance between PVT and PVT. This is fun. Okay. So, we want to be able to see someone standing with an eye height of 3.5 feet wants to be able to see something at an elevation of 2 feet. Right? So 3.5 feet is what? Here? We're assuming that's your driver eye height. Right? That's probably a little low for most everybody, especially if you drive a truck. If you drive like a little sporty car, you know, even a little sporty car is going to be a little higher than that. So this represents the eye height, and this represents the object height. So someone whose eye level is here needs to be able to see something 2 feet off the ground, downfield. Right? What does 2 feet represent?
Like as small as possible, like living thing maybe that could be crossing the road.
No, I mean there's squirrels and there's raccoons and there's possums.
What, tail lights?
Yeah, it's like the bumper.
Yeah.
So the idea is that you should be able to see someone's bumper. Right? That's 2 feet. 2 feet is there. Even on some low cars, that's not, you know, that's pretty low for even low cars. Also, the general assumption is smaller than 2 feet, go ahead and kill it.
That's true.
Raccoon, smaller than 2 feet. We're not designing to save raccoons. Not what the road's for. So, raccoon is in trouble. That's not to say that a raccoon won't mess up your car and cause some damage. How about a ladder? Ladder's smaller than 2 feet. That will mess up your car. But will it kill you?
No, unlikely. Unless you're on a motorcycle.
Unless you're on a motorcycle. In which case, anyone who's on a motorcycle is taking their life in their own hands anyway.
Yeah.
I think that's wild stuff. Knowing what I know about traffic, people that ride motorcycles, wild stuff, man. You put your life in somebody else's hands. So the idea is that you can hit something that's 2 feet tall and not die. Now, the thing that you hit's not going to live, but so that's how roads are designed. Now these are set by the Green Book. Right? If the Green Book came out tomorrow and said you had to design for a 3-foot eye view and a 1-foot object height, then that would change a lot of the regulations of the road. Yes?
So if that were to happen, what would happen to all the current roads designed on the previous Green Book?
They would have to be updated. They have to be updated. They'd be grandfathered in, right? Just say new roads have to be built to this new standard. It's typically how you address those issues. Right? So a driver's eye height must be able to see an object that is 2 feet tall. If the driver can see over the crest, and the sight distance is greater than the length of curve. Here I can see over the crest. Right? Sight distance is greater than the length of curve. Right? If the driver cannot see over the crest, right, the crest is in the way, then the sight distance is less than the curve. These two cases will affect how the curve is designed. So if the curve is gradual enough where I can see over it, or if the curve is steep enough where I can't see over it, those are two separate design criteria. Sag curves. Same definition, allows downhill ample sight distance. Right? A vehicle's headlights are assumed to be at 2 feet above the road. The beam is assumed to have an upward divergence of 1 degree. The driver can see, if the driver can see beyond the curve, the sight distance is greater than L. If the driver cannot see beyond the curve, the sight distance is less than L. Okay? So, let's see if I can draw Grandpa's Buick again.
So that slide that we covered before this was for crest curves?
Yeah. Grandpa's Buick. Looks good? Okay. Here is the center of the eye height, we're assuming that this is 2 feet, right, between here and here, yeah? And then from here, we have a 1 degree divergence. Right? So as you're going downhill, it's illuminating in front of you 1 degree. Okay? Again, that's our design vehicle. Right? If we were designing this road for only truck traffic, we could use a higher eye height, right? Or a higher headlight height and everything else. Right? Now they have the cars that have the headlights that kind of like swivel up and down or whatever, I don't know. Right? That changes things. That provides you more than the minimum requirement. As of right now, these are the requirements for curve. When you calculate the L, or when you're designing a length of curve, it gets rounded up to the nearest 5 foot increment. Okay? So we talk about 2 different curves, Crest curves and Sag curves. And we talk about 2 different situations, where the sight distance is less than the length of curve, when the sight distance is greater than the length of curve. Yeah? Therefore, there are 4 equations that govern. Right? So, if you have a Crest curve, and S is less than L, you design L like this. If you have a Crest curve and S is greater than L, you use this one. Sag curve, S is less than L. Sag curve, S is greater than L. Yeah? Pretty basic. Pretty good? So far? Typically, students mess this up by choosing the wrong one.
On an exam, will those be provided to us? Or?
Yeah, so on the exam, I'm just going to provide you the FE reference manual, and it'll be good. That way, when you take your mechanical FE, you can just go to the civil section and answer all those curve questions, get 3 points.
Easy.
Easy, stupid easy.
3 points.
Yeah.
Pretty good.
Okay? Oh, all right. Another important distinguishing factor here. A, this variable here, is the algebraic difference in grades. The absolute value as a percent. So 2% and negative 3% A equals 5. Not 0.05. And not 1. Good? Algebraic difference. This is pretty much, I think this is the only time that we'll be representing A as a whole number percent value. Or as grades as a whole number percent value. So that goes here, and here, here, and here. So it's an all. Okay. So there's another requirement for Sag curves that isn't necessary for vertical curves, or Crest curves, sorry. Right. Sag curves, you're coming down the road, and there's a part of the momentum of the vehicle that is going in the direction of travel, yeah? You're downhill, gravity's pulling you down, you're driving down, right? Then when you change grade, if you were to come up quickly, it's uncomfortable. It could be, depending on how steep the curve is and how fast you're going, yeah? You kind of get like that, like butterflies in your stomach, or weightless feeling, or whatever. So we want to avoid that, right? So we have a Sag, a comfort requirement for the Sag curve, right? And that is to say that you might be able to see adequately, and you might be able to bring your car to a stop adequately, but we don't want you to experience this feeling of discomfort, which may cause you to either slow down or swerve or brake or something, right? We don't want to present you with anything that is not expected. Yeah? It's one of the fundamental rules of traffic engineering. Don't surprise your drivers. So a funny feeling when you drive is not a good thing. So this is like a check. Generally, you're fine on this. If you're providing adequate sight distance, generally, it's good. However, there are some situations where mathematically it works out. So the length of vertical curve must be at least this long, and at least the length of the other one. So you take the longer of the two. Yeah.
So, like I've noticed that sometimes you can get that when you're going over a crest sometimes too. It doesn't like make me uncomfortable, but it definitely is sometimes
Trying to get some air.
Yeah.
Yeah.
Well, not like air, but I mean, it definitely feels like, you know, there's a change in, you know,
Yeah.
the gravitational, you know, your,
That's like like if you were to take a Crest really fast, you would, you'd come up off the suspension a little bit, yeah.
Is that like a factor at all? Do they take that into account or not so much?
No, not really. No. Let's see if I can draw this out. Here, here, here. This is your car. This is your car. This is the hill that you discussed. This is G1, G2, G3. Yeah. PVI-1, PVI-2. We have another hill that's here. Yeah. These hills might be too close to each other, giving you that odd feeling. You kind of overlap some. That you're probably driving too fast. But in order to get this vertical curve, we have to have a sag curve first. Right? So generally, curves come in really in groups of 3, because there's another curve right here to level, even you out. So it might have something to do with this compound vertical curve that you got going on. Okay. All right. So the length of curve is PVC to PVT, straight distance. We station along the length of curve. Yeah. So the station for PVC equals the station for PVI minus 1/2 L. It's right in the middle. The station for PVT equals the station for PVC plus L. Okay, you go from PVC to PVT, just add L. Right? PVI plus 1/2 L equals PVC, whatever. You get the idea. It's right in the middle. Okay? This is true for vertical curves. It is not true for horizontal curves. Horizontal curves, you have to take the tangent out and then add the L back in. I add emphasis there because not everyone, but every year I get a lot of wrong answers that are specifically on this, or they do this for horizontal curves. This is only true for vertical curves. It's true for vertical curves because we station in the plan view looking down, and there's no difference on a vertical curve in the plan view, right? Because we have to add in, because in a horizontal curve we actually have a curve, we have to take out the tangent and recalculate the stations. There's no recalculating the stations on a vertical curve. Yes?
Will these formulas be on the FE sheet, or do we have to remember these?
I don't think these are on there. I don't think those are on there, the PVC, PVT stuff.
Do we get a note card to bring in?
No, I might have written it on there. I'll look at it, we'll see. Okay. Anybody have any questions about this? Is everyone clear? We all understand that this is not how you do horizontal curves. Good. All right, let's get party started. All right, the Crest vertical curve has a PVI at station 1, 2, 3, plus 4, 5. With an elevation of 345.67, the design speed of the road is 55 miles per hour. G1 is 3.95%, and G2 is negative 4.25%. Find the station for PVC and PVT. Plug and chug, super easy. My grandfather did drive a Buick. Looked just like that. Okay, so we have this grade, and this grade, and this curve, and G1 equals 3.95%, and G2 equals negative 4.25. Okay, this is PVI, that equals 1, 2, 3, plus 4, 5. This is PVC, and this is T. And this is at 345.67. Okay. Okay. What are we doing? What's the first step? Yeah.
Use the relationship formulas to find something out, or not
You
yet?
find the length.
You find the length of curve. That's really the only question. Okay? So we need to use one of these equations. Well, these equations have some variables in them. Yeah? First, is it a crest curve or a sag curve?
Crest.
It says crest, it's a crest. Right? So then we got to find out if S is less than L or S is greater than L. And in order to find S, we need A. Well, we have A, so we got to find S. Yeah? So we'll say find S. That is to say, i.e., find the SSD, stopping site distance. Yeah? Okay? That looks like a weird brain. Got it. I would be terrible at charades, just so you know. Sorry, that's the way it goes. Okay, the stopping site distance is equal to 1.47 times the speed times the time perception reaction plus the speed squared divided by 30 A G plus or minus G. Yeah? Okay? Equals 1.47 times the speed of 55 times 2.5. Why am I using 2.5?
It's the minimum required.
The green book says so.
Yep. Green book says so. I like it.
Is the assumed reaction time.
What G am I using?
The algebraic difference?
Well, there's two grades I could use. Well, how many grades are there I could use? Is there two? I think there's 4 grades that I could potentially use. As I'm driving this way, 3.95 is a positive grade. And then negative 4.25 is a negative grade. It's 2 grades. However, if I were on the opposite side of the road and I'm driving this way, and 4.25 is a positive grade, and 3.95 is a negative grade. So there are 4 potential grades to use. Right? Now, if I'm going uphill, that's going to help me stop. So I'm definitely not going to use either one of the positive grades. The question is, I have 2 negative grades. Right? And which one do I design for?
The worst case.
You would think, but no.
Really?
Yeah. They would say that that would be over-designed because half the people aren't even using it.
And we've already like put worst case scenarios all over.
We've got a lot of built in there. So it's typically rule of thumb that you use the negative of the less extreme of the 2.
Okay.
Right? So I assume both of these are negative. I have 3.95, negative 3.95, and negative 4.25. Negative 3.95 is the less extreme of the 2, so I would use that one. Negative 0.0395. Of course, I hit myself in the face with my mask. Okay. What's the answer, Tate? Do you need glasses or do you? Can you guys see this?
The red's
No.
hard to see.
Yeah, it's
The
not
red's
hard.
really hard to see.
Why don't you guys say something?
Yeah, the red's hard to see.
I can see it just fine.
It's small. Oh, this marker's not very good at it, so you're stuck with it.
I think I would.
Victoria, can you see? It's because you have good eyes and you're young. Well, you can see it? Yeah. So Tate just needs glasses,
Guess so.
We're curious.
Who's got an answer?
Is this supposed to be 11.2?
11.2 divided by 32.2.
Just draw the dot. That's it.
529 feet.
529 feet. Do we round this?
To the nearest 5 foot
To
increment.
the near, we'll round it up to the nearest 5 foot. Okay. It's my stopping sight distance. That's what I need to maintain at all times. Rule of thumb, stopping sight distance, all things being equal, not really, kind of, sort of, should be like 10 times your posted speed. Or 10 times your design speed, sorry. Design speed was 55, we got 530. Not always true because there's grades and there's this and there's that, blah, 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 blah. But gives you an idea that you're in the ballpark. Okay? So, now what?
You had your ask for your equation.
Plug it into what?
Both of them.
And see which one's true.
Yeah.
Yeah, that's it. So, now we just make an assumption. We just assume that S is less than L, calculate L based on our S, and then check to see if the L we calculated is indeed greater than S. Yeah?
Yeah.
So, students will mess this up sometimes. So it's always good to just write everything down. So let's just say step 2. Assume S is less than or equal to L, or S is greater than L. 3, calculate L. Step 4, check assumption. Step 5, recalculate if needed.
So use the other equation.
Yeah, and also check that one.
Yeah.
So, we have our SSL. I love these classes. And everyone can see it's wonderful. Okay, so SSD equals 530 feet from the previous board. And then let's assume, and write it down, S is less than or equal to L, so then we assume that L equals AS squared divided by 2158. Where did 2158 come from?
It's a conversion factor.
It's a huge conversion factor, because we assumed the eye height of the instrument, and we assumed the height of the thing that it's okay to hit, right? So based off that geometric relationship, it comes out to 2158. Okay? If you're really interested, it's in the book, if you can find the book. Which, if you Google hard enough, you will find the book.
It's like 3 minutes.
I'm not saying that you should be Googling copyright infringement, but I didn't post it.
It's on the internet. It's on the internet. It's free.
That's what Abraham Lincoln said. quote, man. Everything you read on the internet is true.
I'm gonna
Quoted
lose
Abraham
sleep
Lincoln.
over textbook manufacturers losing my business.
That's the way she goes. That's the older version anyway. Until they update the green book on the geometric stuff, we'll continue to use this older version of the book. I don't need you guys to spend a bunch of money that you don't have on something you barely need. Sound good?
Didn't they copyrighted telegrams? Like somebody was like listening in on the Morse code and
Okay, what is A equal to? A equals the algebraic difference in the means as a percent equals the absolute value of 4.25 negative minus 3.95 equals 8.2. So L equals 8.2 times 530 divided by 2158. 530 squared, tall.
Or 138, sorry. Yeah, it's weird, I don't know. I don't know if I did that right.
I don't know if you did that right.
1067.
1067 sounds really good.
Yeah, maybe it just. Yeah, 1067, I wrote.
1067 feet. So that was step 3, calculate L. Step 4 is check it. We said that S is less than or equal to L. We said that S was 530, and that was less than or equal to 1067. Is this true? Yes. Yay. So what does L equal?
1067.
1070.
1070.
Will. We round up to the nearest 5 foot increment. If this was not true, then we would have gone back and used this other equation.
And one of them will always be true, not both.
Yes. Anytime you see it in this class. Reality is a funny way of finding the outliers. Any question? Good. Okay, what's next? Now we actually get to answer the problem.
Now we got that.
70. STA PVC equals STA PVI minus 1/2 L equals 1, 2, 3 plus 4, 5 minus 1/2 1070. STA PVC therefore equals 535. 118 plus 10. No, it's all right. Help me out here. Am I correct with that? It's because I thought that was 2. No.
I think you were right.
Yeah, 10. I was wrong in questioning myself. That's where I was wrong. No. There we go. Okay, and then we'll say STA PVT equals STA PVC plus a whole L equals 118 plus 10 plus 1070 equals 128 plus 80. Good? Fairly straightforward. Yeah. Do we want to do the Sag one? We should do the Sag one.
The second.
Yeah, second question. The second example is the Sag question. All right, we'll do the Sag one. So this was vertical. Let's go with Sag. The Sag curve has a PVI at station 5.4 plus 3.2 with an elevation of 76.54. The design speed of the road is 45 miles per hour. G1 is negative 3.5% and G2 is 6.15%. Be sure to check for the comfort requirements. Station for PVC and PVT are what? So for sag curves, then this step 6 would be Sag Comfort. If needed. Alright. So I'll get rid of this. Michelle has this by now. Okay. So here's the sag curve that we're talking about. PVC, PVT, PVI equals 4 plus 3.2. And 7654. 76.4 feet. Yeah. And what else? We have the G1s. 1 equals negative 3.15. G2 equals 6.15. Very steep. Generally, we don't like to see grades above 6%. On rural roads, it's more acceptable, but on urban roads, we try to keep it 6 or below. Because trucks don't like stopping on grades. It's not good for them. The brakes heat up and stuff. So the assumption is in urban areas, trucks are more likely to be stopped than in rural areas where they can accept the higher grades because they're not stopping. However, you put trucks on grades long enough and they start to affect efficiency because they go to like crawl speed and things like that. Okay, there's our curve. Let's do our sight distance calculation. All right, sight distance equation is still the same, but it's 1.47 times 45 plus 2.5 plus 45 squared divided by 30, 11.2 divided by 32.2. What is the grade that we'll be using?
Negative 3.15.
The grade is negative 3.15. Why negative 3.15?
It's the lesser of the two extremes.
We take the negative, and we take the less extreme of the two negatives. Everybody understand that? Yes, me, I see furrowed brow.
What do you mean by extreme?
Okay? So, if we're driving from this way, we experience negative 3.15 and a positive 6. Yeah? If we're driving this way, we experience a negative 6 and a positive 3. Yeah? So, there's 4 grades that we have to consider. The negatives and positives of both of these values. Immediately get the positives out of there because they're going to help us stop, and we don't want to count those. So then we have the choice between negative 3.14 and negative 6.15. We take the one that is less extreme. I say less extreme as in the one that's greater, but we're talking about negative. You know what I mean? So it's easier for me to say the one that is less extreme than the other one because it conveys the idea that I'm trying to. I say, then you, not assuming the positives, right? If I say take the greater one, well then you just take the positive 6. Take the negative, look at 2 negatives, and you take the one that's less extreme of those. Yep. You're not the only one that had that question, but I just called. Yeah, everyone get that? Questions? Okay. Okay, so I'm gonna take negative 0.0315. Why is it 0.0315? Converting percent to a grade, or the grade percent decimal, blah, 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 blah. Well said, huh? Very articulate profession you got, yes.
Why is it 3.15?
It's 3.5, but.
Is it 3.5?
Yeah,
Sorry.
I've just been going on that, just so.
That was a test. You nailed it.
Didn't you write 3.15?
I wrote 3.15, yeah. It's 3.5.
It's not a big.
0.4%.
Sure, than 5%.
Look it around anyway. Tomato, potato. So I gotta see you're laughing at my own jokes. What is our sight distance? Tate's on the job, assuming he can see the board.
From what I can see, I got 385.
385?
Yep.
390.
Whoa.
No, I already, well,
You're-
381.
There we
It's,
go.
yeah, he already rounded it.
381 approximately equal to 385. Is that good? Anybody else?
Forgot 85 is the decimal.
Killing me small. Yeah. 385 it is. Okay. Step one, done. Okay, now we gotta calculate A, which is the absolute difference between the grades, which is 6.15 minus negative 3.5.
$9.65.
9.65. Let's go. Okay? Okay, so good, find S. Now we're gonna assume that S is less than L, sure, why not? So I generally assume that S is less than L to begin with because these equations are kind of easier to work with than these. Just in the calculator, it doesn't really matter. So we'll assume S is less than L. And then we'll go with, we're going with this one or this one or this one? Bottom one. Why are we choosing the bottom one? Because it is a sag curve. We're assuming S is less than L, so we're taking this equation. L equals AS squared divided by 400 plus 3.5 x. Yep. L equals 9.65 385 squared divided by 400 plus 3.5. What do we get?
819.
Anybody else get that?
Mhm.
819. 819. So then we're going to check. We said check. S is less than L, and then right underneath that, I'm going to put 385 is less than, is this true? Woo-hoo. Yay, yes.
Bless you.
Thank you.
What does L equal?
820.
820. Okay, then we do,
For comfort.
oh, yeah, we gotta check comfort. See, there you go, I'm already messing it up. L comfort. L equals A V squared divided by 46.5. Okay? I know what I did that, okay. 9.65 times 45 squared divided by 46.5. Now equals
420.
420 feet. Is that right?
On the dot.
Nailed it. Okay. So which L do I use? This one or this one?
Whoa.
Oh, wait.
What's a safer curve? A longer curve or a shorter curve?
Longer.
And the curve must be at least 820 feet to provide adequate sight distance, thus surpassing the requirements of this.
So that's like a minimum.
This is the minimum. It must be at least 420 to provide comfort. It must be at least 820 to provide sight distance. So we have to provide both. So by providing 820, we're clearly providing more than the required 420. Okay, so yeah, station for PVC equals station for PVI minus 1/2 L equals, ooh, that's not it. 5,4 plus 3,5 minus 1/2 820. And 0 plus 25. Right, and then PVT equals station PVC plus L equals 5 plus 25 plus 820 equals 5, 8 plus 4, 5. Good?
It's just like the first level of the.
Yeah, this is level 1.
Alright.
Don't worry.
That's a pretty good, right?
Don't worry. Hard math, right?
Good, okay. Next, let's talk about the elevations. So now we got the stations, we're gonna talk about elevations next. So, the station for the elevation of PVC equals the elevation of PVI minus G1 L over 2. That just means we're taking this elevation and we're going backwards along the grade half the distance. So if you think about it as a triangle, where this is PVI and this is PVC, and this grade equals G1. Right? We're going back, and this distance is 1/2 L, and we're subtracting out this distance here. That's what this equation is doing. So if the grade is a negative, takes care of itself. You just put the negative grade in there, then you're adding the negative, and you're actually adding the difference, whatever. Right? The station for PVT equals the station for PVI plus G2. G2, that gets you to here, right? So we're completely ignoring the fact that it's on a curve right now. We're just taking the grade and the tangents. Yeah? Sound good? We get into trouble when we start trying to take the actual grade of the road between the curve, between the PVI, PVC, and PVT. So this is the generic for any elevation along X. We start with Y PVC, we start at this elevation, we add to it G1X. G1X gets us to here, this elevation here, and then this parabolic function brings us down this little bit. So to get to this elevation from PVC, we take PVC, we add G1X, that gets us to this elevation, and then over here we're subtracting out this little bit to get us the elevation here. Okay. All right. We'll pick up here on, we'll pick up here on Thursday. How about that? All right.